Eric Burgess here, and today we've been asked about confidence intervals, this thing. In this video, we're going to cover the Z and T, how to tell if the confidence interval that we're looking for is a T confidence interval or a Z confidence interval. Then we're going to do the confidence interval. We're going to do it using well, first let's do it using the formula. So we're going to do it using a formula and a chart, and then we're going to do it using the calculator. And then we're going to do it using Excel. And Citrus provides you Excel, and often it's much better than the calculator. So I highly recommend getting good at Excel, because when you start dealing with data and things, Excel has a couple advantages. In this particular problem, though, the calculator is probably the easiest way. So let's go ahead and just dive right in. So first off, we know we're dealing with the confidence interval because that's our title, but also because they ask for one. Find the confidence interval. It's right here. So to find the confidence interval, what we would say is, okay, well, the confidence interval, we want to know if it's a Z or a T one, right? Because we know that if it's a confidence interval, there's that. There's also a proportion. Proportion confidence intervals are also Z. So the way you tell is if you're given a sample standard deviation or a population standard deviation. If you're given a sample standard deviation, we're going to use a T-score. If we're given a population standard deviation, we're going to be given a Z-score. And so in this case, we can just really quick read this and see what we find here. So let's go ahead and write down the numbers too as we go. I find that pretty helpful. So we have a study of 30 randomly selected employees of a company. So we say, okay, we got 30 randomly selected employees. That's going to be N. That's how many people we asked. It's our sample size. And it says 30 randomly selected employees of a company showed that the mean distance that they travel from home to work is 14.8 miles. The key word here is mean. It could say average, but we see that the average distance one of these workers travels is 14.8 miles. So that's how long their drive is to work. And we know that this mean came from a sample of 30 people. So this is an X bar. It is not a mu. I see that as a common mistake. We are trying to actually estimate mu. We'll get to that in a second, but we're just kind of writing down numbers, getting information from the problem. The standard deviation was 1.2 miles. And so we say the standard deviation, it does not say population standard deviation. So that means that this standard deviation must go with our sample of 30. So it has to be an S. And that's 1.2 miles. You'll know if it's population because they'll say it's population standard deviation. So we know that therefore, this is how you write therefore in fancy math language, that we are going to be using a T-score. It's not a Z-score. It's going to be a T because we have a sample standard deviation. All right, next up it says, find the 95% confidence interval of the true mean. So we want the 95% confidence interval of the true mean. What does that mean? Well, we have a sample mean here. We have a sample mean that applies for these 30 people that we asked. But let's say that our company has 700 workers. We want to be able to use these 30 people to say something about these 700 workers. We're making another assumption here that's not stated directly in the problem, but we're assuming that the data is normally distributed. Okay, I'm not going to go into too much depth of what that implies and means, maybe in another video. But basically, if we draw a normal curve, what we're saying is it plays by the rules of a normal distribution. And this should look symmetric. Sorry, mine always look asymmetric because I'm not that great at drawing normal distributions. So what we're saying here is the mean is in the middle. In a normal distribution, the mean is the most common value. And then as we go further away from the mean, values become less common. They don't happen as much. And it kind of makes sense. A lot of things behave this way. Like if someone has a 60-mile drive to work and the average is 14.8, they're going to be very unlikely. They're going to be super far away from the mean. Or if they live right next door and their drive is a mile, that's going to be way down here, 1 mile. They're going to be super far away from the mean that's 14.8 miles. So it's going to be very unlikely. So we're assuming that our data works according to this thing. And when we say that we want to be 95% confident, we're saying that there is a value, there's a range of values. There's some lowest value and some highest value, and all the values in the middle that we would be really sure. Because remember, when we say a 95%, we're saying 95%. So if the mean is here, we can go up and down by 95% over 2, right? Because there'd be half, this would be split in half. So 95% over 2 would be right here. And 95% over 2 would be right here. When you add them, you'll get 95%. And we're saying that the true mean of the population, that guy lives somewhere in this 95%. That's what we're estimating. So the formula actually has, right? There's the true mean. And remember in math, this is how we write, there's something that's less than this true mean, and there's something that's more than this true mean. Because we didn't ask all 700 employees, or however many employees there are, we only asked 30. There's going to be this realm that we're not quite so sure if the true mean is over there. Like it could be over there, but we are 95% sure that it's not. And those regions are right here. It could be these really high and low values. Seems very unlikely that the true mean will actually be over there. And the reason we have this is because we only asked 30 people. So those 30 people we asked, they could all be weird people who live like 50 miles away from work. And we could get some mean that's just not really the average. It's not really what all 700 people would be like. But 95% is pretty high, pretty safe bet that it's a good estimate. And so what we would say is we would say, okay, there's a true mean. We want to estimate it. And so here's our mean. It's in between two values. And what do we have for our mean? Well, we have this guy, right? It's this mean. So we have an X bar. And what we do is we do something pretty clever. We say, well, there's an error. There's a mean plus an error. I'm going to write E for error. So there's an error because we only asked 30 people, right? And so the mean plus this error, or actually I have this backwards. This should be a minus. So below the mean, so to estimate it, there's going to be a value below, and we'll take the mean minus the error. That'll give us the lowest value possible, right? Because we took off all the error. And then we have a value plus the errors. And then what we have here is we have the error. We have to define what that is. How do we figure out the error? Well, we know the error is going to be related to this curve. In this case, we know specifically it's going to be a t distribution. So we use a t-score. And the t-score, if we want to be 95% sure, that means that there's 5% remaining in these tails. We call these the tails of the distribution. So that when you combine both tails, so we call it two tails, there's 5%. So this is an alpha of two tails. Is equal to 5%. Sometimes though, we only have an alpha of one tail, and things are commonly expressed in alpha of one tail. So we might say that it's a two-tail test, and in one tail, so alpha of one tail, that's half of this, right? Because the distribution is symmetric. So there's half of the 5% here and half here. So we would say that it's 5%, which is 5% over 2. We divide it in half. That's the same thing as 0.05 over 2, which is equal to 0.025. You could plug that in the calculator if you want, but that's what it is. So we would say our alpha is this thing. And we're going to use this to get our t. Because what we want is we want the t-score that corresponds to this and the t-score that corresponds to this. And then what we're going to do is so we have our error is equal to this t-score, and we're going to scale it by our sample data, our statistics. So we have here a standard deviation that describes the spread of our data. So if our data is very spread out, or if we don't have very many points, this spread is going to have a big influence on our data. But if we have a lot of points, the spread won't matter as much because we have so many points that we'll have a good average. Like if we ask 600 people, it's going to be a lot more accurate than if we only asked 30 people, depending on what the total population is. It might not matter that much in a bigger scale. So we're going to divide it by the square root of the number of people we asked, or our sample size, n. So what we're saying is the spread matters a lot more if the sample size is low. Let me show you kind of why that's true. So if the spread, let's say that the spread is 1.2 like we have here, but let's say that when we do the square root of our sample size, let's say we had a sample size of 10,000. That's going to be a really, really big number. In fact, let's go for like 1,000,000 or whatever it is, however many that is. 1, 2, 3, 1, 2, 3. Here we go. 1,000,000. So here's 1,000,000. This thing is going to be nearly zero. Like if you had a piece of pizza and you split it into 1,000,000 pieces, if you divided it by 1,000,000, there's going to be like the pizza will be like dust. There's going to be like no piece of pizza left. That's kind of what this is saying. But if you're going to split a pizza into only 2 pieces, those pieces are going to be huge. You're going to just split the pizza in half. So that's how we estimate our error. Our error will be big. It's going to be a bigger number if n is small. If we don't ask very many people, we're going to have a lot more error. But if we ask a lot of people, we're not going to have very much error. So if we were to write this formula out completely, it would be the distribution factor, when we're getting this from a table, times s over the square root of n. And then we're saying that, so this is the mean minus the error, like we have up here. So this value is going to be below the true mean. So this is our lower estimate. And remember, this is a population. We're saying something about the entire population using this. And then we're going to have x bar plus this error. So it's going to be the same expression. It's just going to be positive this time. So we're going to have s over the square root of n. That's where this formula comes from and why we have it. It's just an expression that allows us to take sample information and estimate the true mean. Now check this out. What if we ask so many people that our error is essentially zero? What if we're trying to find something and we find that the error is basically zero? Well, look at this. If it's zero, that means that this and this are zero. So the mean minus 0 is just the mean, and the mean plus 0 is just the mean. And we get that the value that we picked is basically the mean. The mean is essentially equal to our sample mean. So this just makes a lot of sense. Like that should happen, right? If we ask a lot of people, we should get a value that is the mean. So that's the idea here. Now, it's often very, very hard to ask a lot of people and get good data. And so being able to have confidence intervals makes it so we can give pretty reasonable statements about an entire population, even though we only asked a small percentage of the population. So, okay, now that we understand our formula, let's go ahead and let's use it, shall we? So using this, we already have the mean. That is simply 14.8. So we have 14.8, and we're going to subtract off of it our t-score. So to find the t-score, we'll do the chart method first. So the chart method, the way we're gonna do it is we're going to find the area in one tail. We already did. It's 0.025, right? Because we had 5% left. If instead we had like 97% confident, that means that there would be 3% left, right? Because we need to get to 100. So we would do 100 minus 97 and we get 3%. And then and since confidence intervals will always have an error below and above, because we're estimating something and we could estimate too high or too low. So we would divide it by 2 to get the area in one tail. So that's just another example if you wanted just another one just to see if it wasn't 95%. So, okay, 95%, we have 0.025 is the area in one tail. So we go to our nifty t-table. And remember our sample size was 30. Let's go ahead and let's move this calculator. Get out of here, you calculator. Was that blocking my... No, it wasn't blocking. Okay, so in here, we have a degree of freedom. Now remember, 30 was our n. And the degree of freedom is just 1 minus that. So we're going to go to 29, which is right here. And here we have the area in one tail. You might be using a different chart. All the charts are the same. They're going to show you the area in one tail. So we had in one tail 0.025, which is right here. And look at this. In two tails, it was 0.05. So you could use two tails if you wanted as well. So what we want is we want the area where these cross. So we're just going to go ahead and draw 2 lines, and we see that they cross right here at 2.045. So we go into here and we say our t-score is going to be 2.045. All right, so hopefully you understand how to look it up in the chart. And this chart's just it's just an integral of what this is. You'll learn about that in calculus. If you've already taken a little bit of calculus and you know about integrals, then that's where those numbers are coming from. They basically evaluated it at different spots. And it gives us this value. So, okay, now that we have our t-score, we're going to do S. Now, our standard deviation is going to be 1.2. We were given that. And our N is 30. So this is going to give us our error, this expression. Then we're saying that the mean, the true mean, the population mean, is in the middle of this. And on the other side, it's just 14.8 plus the error, which is all of this stuff. We already found it. So it's going to be plus 2.045 times 1.2 over the square root of 30. When we do this, we're going to get a number. Now, pay attention to this part because I see a lot of people use their calculator in sort of not the most efficient way. Now, if you don't have a calculator that can type like proper fractions, then you're going to have to evaluate this in order. So you'd have to do the square root of 30 first, then do 1.2 divided by that, and then multiply that by 2.045, and then do 14.8 minus whatever that is. So that's just order of operations, kind of assuming you already understand how to do that. But I'm going to show you how to enter this all in at once if you have like a calculator that can type fractions, which this one can. Now, some of you guys, your calculator might not be updated, so it actually can't. So you have to do that process I just described. But Citrus College has like calculators, the new ones that they hand out in classes, they can actually all do this. So we've got 14.8. So we have 14.8. And we want to do minus. Don't use the negative sign. Use minus. And we have 2.045. So we type in 2.045. And then type this literally exactly as it looks. So we have a parenthesis. So we put a parenthesis. We have a fraction. So a lot of you guys will use the division key, but check this out. If you go up here, there's this green F1. This is your first function menu. I'm not exactly sure the fancy names for these, but I'm pretty sure it's just function 1. It's green, so we're going to hit the green key and get to it. And it actually has fraction abilities here. So you can convert from fraction to decimal. But here we have numerator over denominator, top over bottom. So we want this one, number 1. It lets us type it as a fraction. So we could type 1.2, come down here and type, we want the square root. The square root is this blue guy right here. So we're going to hit second to get to the blue one. Square root, and then 30. We're going to push over. Now we got out from underneath the radical, but we're still under the fraction. So we have to go over one more time. And you see we're over here. So now we can close the parenthesis and hit enter. So that's our lower value. So this whole thing right here becomes 14.35. And then we have our true mean. So that's the lower value. The mean cannot be any lower than this. As low as we go for 95% accurate, right? Because that's how we got this number. We used the 95% to get the t-score. So now we're going to go ahead and do the positive side. It's really easy on the calculator. Just come up to this and highlight it and hit enter. And it brings it back up. And what you can do is you can actually just come over and you can just change this to a plus sign. So we hit plus, and we hit enter. And you get the upper range because remember, it's just the same expression just added. So we get 15 point, let me move my mouse, 25 if we round. All right, so this is our confidence interval. This is the average. This is the average. This describes a 95% confidence interval. What we're saying here is that we are 95% sure that the average commute will be, the true mean of that will be between 14.35 and 15.25. That's what we're saying. So if someone has an average, if the average commute, if we ask 30 more people in the company, the value that comes out for the mean is going to be somewhere in this range. We're 95% sure. If you end up asking 30 new random people from the company and the average ends up being like 17, there was only a 5% chance that that happened. So it's very unlikely to happen that it would be outside the range. So if the average commute's actually 17 miles, then that's really, really unlikely that that happens. So let's go ahead now and dive into another way to do this. So you can actually just use the calculator's built-in functions. If you go to stat and go over to tests, there's actually a t interval that you can use. So once you identify that you have to use t, we can just use t intervals. So let's actually scroll up here so we can see our values. So I'm going to go ahead and use that. So you can hit 8 or you can just go to it and hit enter. And it has two modes. So you could give it data because, right, these statistics over here, this S and this X bar, they were calculated using our data. So that's why we call it a statistic. And we could have just raw data. And so you could compute these yourself and we could just give that to the calculator. But we have the actual statistics that we need. So we're going to go to stats. And then for our X bar, first statistic is 14.8. Our standard deviation is already been calculated is 1.2. And our N is 30. How confident we want to be? Well, we want to be 95% confident. See, it doesn't ask for alpha. It asks for your confidence level. And then we're going to go to calculate. Don't forget to convert your 95 to a decimal too. And here we go. So this is given as interval notation. If you're not familiar, it's just a way of writing that we start at this point and we go to this point. So it includes all the points between these two values. So it goes from 14.35 to, in this case we rounded, which is what we got with our formula, to 15.248, which again, if we round, we get the exact same thing. So this is another way to do it. This way is extremely easy to do. And then finally, there's a way to do this with Excel. So what Excel does is Excel gives you E. These guys. Gives you E's. So we still have to do the adding of the mean and subtracting of the mean, or the adding and subtracting of the error to the mean ourselves. So we're going to use Excel to get these values, and then we're going to use the mean to find the lower and the upper. So let's go ahead, open up a fresh Excel. So here's Excel. And the first thing we're going to do is let's name this first thing. We're going to call this the mean. And the mean that we had, what the heck did we have? We had 14.8. 14.8. The next thing that we have is we're going to have a lower estimate. We're going to have the true mean in the middle. And we're going to have the upper estimate. And then right here, I'm just going to type in I can't type mu, so I'm going to type it like this, just an M. And then these are actually less than or equal to and greater than or equal to. So in Excel, that doesn't look too amazing. But basically, we're saying that mu is in the middle. Now the lower, we want to write in a function. So we're going to type equals to let it know we're going to be doing a function. And then we're going to type t.confidence, or it might be confidence.t. I always get it mixed up. Confidence.t. If you can actually just navigate to it and hit tab, and it will type the rest for you, or you could just type it all out. But we have confidence.t, and it wants an alpha. Now this alpha that it wants is the two-tail alpha. So the two-tail alpha, we wanted to be 95% sure, so that left 5%. This is like the unconfident interval. Like this is how much we are not confident on the ends of the distribution. And then our standard deviation, well, we have that. That's just 1.2. And we want the size, which is 30. Now, take note that we actually don't need the mean for this. And that's why we have to add and subtract the mean ourselves. So if we do this, we're going to get a number. This is the error that we get. I also just realized that I made all these things over 1. So I'm just going to really quick move them over. You Control X to cut and Control V to paste. And this is our error. So this lower value is going to be the mean plus error. And if we want to type that in here, we say we want to do a calculation. So we type equals. And then we want to use the value in A2. You could just type 14.8, but I encourage you to get used to using the cells. So just value in A2, we want to add to it the value in B2. We just click it. And there's B2. And when we do that, we get, oh, whoops, this one we want to be a minus. So we're going to change this to a minus because this one's going to be the lower value. I have screwed things up here. Yeah, it's angry at me now. And I'm actually going to leave this in because this is something that I do all the time. And I feel like you guys could get messed up doing it. You just delete that extra one. Sometimes you'll accidentally click around and it will insert cells you didn't mean to put in. It can be a bit frustrating at times. But there we go. There's our lower value, and we're going to update this to be a minus sign. And then the upper value will be the mean plus the error. We're going to go ahead and extend this out. And this is simply going to be the mean. So we're going to type equals because we want to do a computation. We're going to do 14.8, which is the value in A2, plus the error. We're just going to click it and hit enter. And there we go. We get the exact same thing. 14.35 on one and 15.25 on the other. So you can actually use Excel for this. Now there was one other question it had for us that we actually didn't finish reading. It's if all workers drive at 30 miles per hour, how much time should they have to get to work? So we want to, based on this confidence interval that we've got here, we want to make a policy decision. We want to say, okay, based on the statistics that we've done, we're going to institute a rule that we know will apply to 95% of the people. It's very, very likely that this is the average. And so we're going to use this to say, okay. Now, they said so what we're saying here is that most people have in between a 14.35 and a 15.25 average drive to work. So they have to drive 14.35 miles or 15.25 miles to get to work. It's going to be somewhere in that range. So we're 95% sure that the true mean's in there. And so we say, okay, we're going to assume they all drive 30 miles per hour. How much time should we give them to get to work? So to do this, let's do the lower end first. So first we have 14.35 is the shortest distance people typically go. And that's in miles. And then we are told up here that everyone's going to be driving at 30 miles an hour. We're just kind of assuming that. It's a safe assumption. It's a lower number, especially if people take the highway, they'll be a lot faster than that. So we're assuming they drive at 30 miles per hour. We want to know how long it takes. Now there's this formula that we can use. It's that distance is equal to rate times time. So this is distance. This is rate. This is time. And if you just look at this formula from a sort of just a logical point of view, if you're going somewhere really fast or really high rate, it's not going to take very much time to get there. But you'll still go the same distance. If you have a very slow rate, and it's going to take a very long time to go the same amount of distance. That's basically what this is saying. It's all it's saying. So we want to know, okay, they have to go 14.35 miles. So they have to go 14.35 miles. And the rate that they're going at is 30 miles per hour. We want to know how long that's going to take. So it's really important to write out the units so you can sort of just see it clearly. So it's going to be 14.35 miles. And this is equal to 30 miles per hour. That's our rate, miles per hour, times the time. And so if we divide both sides by 30 miles per hour, the miles per hour flips. So when you divide, we'll divide by 30 miles per hour and 30 miles per hour. These cancel out because that's just one. And we're left with 14.35 miles times, and what we're going to do is we're going to flip the miles per hour. So it's still going to be divided by 30. In fact, we can write it out a bit differently so it's a little more clear. When we flip it, because the way we divide a fraction by a fraction, because this here is a fraction, is we multiply by the reciprocal, because if we do that, it'll be hours and miles, and those will cancel out. So what we do is we take this, multiply by the reciprocal. 30 is 30 over 1. So the flip side is 1 over 30, and it's hours per mile. And this is really like miles over 1. So these cancel, and we're left in just hours, which makes sense. We should only have time left. And it becomes 14.35 divided by 30, because when you multiply, the 14.35 will come up to the top. And so let's go ahead and find that. We're going to do 14.35 divided by 30. So this is the amount in hours, but in order to go to minutes, there are 60 minutes in an hour, right? So what we're going to do is we're going to multiply. There are 60 minutes in 1 hour. The hours will cancel because there's an hour below and an hour above. And we're left with this value times 60. So it's the answer, which is whatever this is, times 60. Then we get 28 minutes. So it's going to be 28 minutes drive, at least. That's the lowest drive. Now for the second one, we can speed this up quite a bit. And we're just going to do the same thing. So it's going to wind up being the upper value, which we call our upper value is 15.25. So we're going to do 15.25 divided by 30 times 60, because that's what we did earlier, right? We divided by the miles per hour, we multiplied by 60, and this is going to give us our time, and it's going to be our time in minutes. And so we're just going to really quick do that. So it's going to be 15.25 and divided by 30. That's equal to that. We're going to multiply by 60. And so that's going to be a 30 and a half minute drive. So we see here that at the lower side, it's going to be 28 minutes. At the upper side, it's going to be 30 minutes. So if I were to recommend how long they should drive, I'd say, we give them a little wiggle room and say, give them 35 minutes. Sounds like a fair amount of time. You got to park and stuff, so maybe even 40 minutes. But you would show this calculation and say, hey, I want to be reasonable and give them some time to park. You could write out kind of your reasoning. But that is how you do this problem. And there's a variety of ways of tackling it. If you have any questions about this, let me know, subscribe, and we will see you in the next video.